Valence bond theory. So valence bond theory is used to explain how various shapes result from the atomic orbital s holding the bonding and non-bonding electrons. If you can recall that electron configuration and atomic orbital diagrams indicate the location of an atom's electrons within atomic orbitals. I was trying to say atomic portals, which wasn't coming. Here we have the electron configuration for the hydrogen fluoride atom that we talked about before. Okay. So if we have unpaired electrons, that's going to mean that we have a free radical and it's extremely reactive. Two hydrogen atoms come together to form your H2. This is the Lewis structure for H2. Your atomic orbital diagram can be drawn for each atom. In H2, two hydrogen atoms share two electrons forming a covalent bond. The electron configuration for both HS in H2 has two electrons in the 1s orbital. This is going to be considered your atomic orbital diagram. Okay, so if we're looking at it in 3D, we have two hydrogen atoms that come together and they overlap. And since the s orbitals are spherical, each hydrogen atom's 1s orbital can be shown as a sphere. So electrons are shared in this overlap between two bonded atoms. Now, if we have, it's quite similar, but it's a little bit different. So we have two unstable, let's call them fluorine atoms, and they do the same thing. But the covalent bond between fluorine atoms on an F2 forms between the two p orbitals and make a dumbbell shape. So as you continue, you'll see different shapes. You have a diatomic molecules, and they are the simplest. Consider the methane, right? CH4. Each carbon in its ground state electron configuration and atomic orbital are actually shown here. Your carbon atom needs 4 unpaired electrons to form single bonds with hydrogen atoms. Now, to get 4 1 electrons from the 2s orbital must be promoted to the unoccupied 2p orbital. Now, to get 4, 1 electron from 2s orbital must be promoted to the unoccupied 2p orbital, like I just said. But given this atomic orbital diagram, the carbon-hydrogen should be different because one forms from the overlap with the 2s orbital to form 2p orbitals. Since 2px, 2py, and 2pz orbitals lie on x, y, and z axes, the bond angles formed from these orbitals should be right at 90 degrees. Your VSEPR predicts geometry is tetrahedral with 109.5 degree bond angle, and that's what they identify that with. The only way to get 4 identical orbitals is to hybridize or combine valence electrons in the 2s and 3p orbitals to get a new sp3 atomic hybrid orbital. So sp3 is equivalent to 1 in the s orbital and 3 in the p orbitals. So to maximize the distance between the electrons, the 4 sp3 hybrid orbitals are as far apart as possible to get tetrahedral and 109.5 degrees matching VSEPR. Your steric number, or what we're going to call the SN, you might see SN of a central atom, can be used to determine the type of hybrid orbital on central atom of molecules or polyatomic ions. You can use this formula to find your steric number in a central atom. Now, these are for central atoms you're finding steric numbers. This table shows you hybrid orbitals corresponding to each shape in steric number. So you can use this very easily along with your VSEPR chart to find those hybrid orbitals that you're going to be looking for. This is pretty close to a VSEPR chart. This is available to you in your handout, and I also have the other one loaded in the D2L. Now, the other one, I would very much suggest that you print that out and bring it with you to class. You'll earn some bonus points for it, and you'll have your handy tool that you need to be able to complete this task. So there are many different representations, and you're going to use all of these, okay? You have straight line bonded in a plane of paper. You have a hatched wedge which is a bond going into that page, and then you have a solid wedge coming out of the paper. And I will be showing you in class exactly what we're talking about when we're talking about bonds in a plane of paper. So you're going to be using models to build ball and stick models of molecules. This is the most common type of model. Each ball represents an atom. Each stick represents a bond between two atoms. And the convention is to use different colored balls to represent different elements. These are most commonly used colors for a few elements and the rationale for each color. You can also use brown or purple as a central atom with 5 electron pairs, or silver and yellow as a central atom with 6 electron pairs. Remember that single bonds are the longest, double bonds are shorter, and triple bonds are the shortest. Now, for our purposes, we'll use the short gray sticks for the single bonds and the longer flexible sticks to make the multiple bonds. It doesn't matter if it's 2 or 3 bonds. Today, you're going to try to finish this lab up. We're going to work together. We're going to get through it, and that's what we're going to do for this week. We're going to fill in our geometries, our bond angles. You're going to be with the same partner you were with last week, and we're going to do this as a group. So if you have any questions, make sure to reach out, and I will help you as much as I can. Good luck.